All right, we're going to be talking about mathematical proofs today. This section has become a large part of A-level maths problem solving. So proofs tend to be the bane of existence for some A-level students' life, and we're going to run you through a few of the basic forms here that they have in the regular A-level maths. So one of the first proofs that we get is proof by exhaustion. And this one you're probably already familiar with. You just essentially run through every possibility to show that it can be nothing else. And it is tedious, as our little friend, the doggy there, is showing us. And this is kind of a reason why you only want to do this as a last resort. So if there's something cleverer to do or something a little bit more sophisticated, you want to try that first to see if it will work. So we're going to start dividing into this because this is actually a classic problem trying to prove something's prime. And it hasn't really been an easy way to do it, and computers still struggle with this, which is why we use primes all the time. But there's a clever way to do this. So first thing, we just start with 2. You divide by 2. You can easily see it's not even, so therefore 2 is not going to go into it. That's our first prime. But that also means that we only have to go up to about halfway up to the prime. So we don't have to try to divide higher primes than halfway, which is 56.5, and because it's not a whole number, it doesn't divide evenly, therefore 2 is not a factor of 113. You essentially have to run through everything up to 56, and as you can see, that we've got quite a few of them up to this point, and hence it's a bit tedious. So hopefully they don't give you something like this on an exam, because it would be a bit tedious, and I imagine a lot of people start forgetting primes around this sort of area here. But essentially that's what you'd have to do. You just have to go through and show that every one of these things. So you'd lay it out, you just start at the beginning and go through each one showing that it doesn't divide evenly. I kind of dotted this because we ran out of room, but if you had to do it, you would show every one of them and go on to the end. Now, a computer can do this quite easily, right? So this is advanced quite a bit more than doing it by hand and by calculator. If you're on a test, you just have to run through it with your calculator. But as you can see, this is why we want this as our last choice, but it still does prove things. Now, you'd always have to make sure that you have a concluding statement. Something like that. These 3 dots here means therefore, so it'd be therefore 113 is prime, proven by exhaustion. So here's another proof by exhaustion, which is a bit harder to understand what to do with this one. So prove that for any positive whole number n, the value of n cubed minus n is always a multiple of 3. Now, if you're trying to do this by exhaustion, you're thinking, that's all of the numbers up to infinity. That's impossible, right? So we have to figure out a more clever way of how to split up all possible numbers. And the clue is essentially with this number here, the one that they're asking about is a multiple of 3. So we're going to run through all possibilities for n based on this question here, right? So the first one is going to be that one of the first possibilities is that n is already a multiple of 3. And then we use this symbol, which is just implies that. So it's sort of like this statement implies this statement over here, right? So they're going to want you to use these as much as possible. So that n is 3 times some number here, right? So we then say that m is also a whole number, right? So that's one of the stipulations from earlier. And this implies that if you put it into this equation up here, that's going to be 3m all cubed minus 3m, which therefore implies that that's 27m to the 3 minus 3m, which therefore, and this is the key that you want to do at the end, that's 3 times the rest of this. So this is the whole thing here times 3, and therefore that is a multiple of 3, right? And so we're going to do this 2 more times to run through every possibility. Okay, so we move on to the next possibility for what n could be. So n is 1 more than a multiple of 3, implies that we have this this formula here, and m is still a whole number that we have here, right? So this is the form of n cubed minus n, which we then substitute this whole piece in for each of those. Now you can multiply this out however you want, but I'm going to show you a different way that's also really good for further maths. So one of the ways that you can get good at expanding these sorts of things is using Pascal's triangle, which looks like this over here, and there's a lot of patterns here, invented by Blaise Pascal, who was another French mathematician and another child prodigy. So his triangle works like this, that each level of the triangle is an expansion of a plus b. It's the coefficients that you're going to get in front of these 2 things. So you get 0, and you're just going to get 1. A plus b to the 1 is going to give you 1a and 1b. And it expands like this. So the next line is going to be a plus b squared, which we know, we've done that lots. It's a squared plus 2ab plus b squared. And then this is the one that we want, but the pattern will continue all the way through. So if you use this enough, you can start to see how this is going to be expanded right away. Okay, so this is the one that we need right there. Okay, so this would be the piece that we need. So you see Pascal's triangle here is 1, 3, 3, 1. And then we expand that where A is 3m from up here and B is 1. And it's going to follow this pattern here. Substituting them in, you get 3 to the m cubed plus 3 times 3m squared times 1. And 3 times 3m, 1 squared, and then 1 cubed there. Just substituting these values in, right? This implies that you're going to get 27m cubed plus 27m squared plus 9m plus 1. And remember, this guy is traveling down with us all the way through here, right? So we don't want to forget about him. And so now we get this line. Make sure you're using the implies bit as well, because this is a proof. And that implies that we get down to, you group everything and it should turn into this. 27m cubed plus 27m squared plus 6m, right? And you can see that there's going to be a multiple of 3 and all that. The 1's canceled here, right? Make sure you're taking that negative sign, multiplying both of those pieces. 1's canceled, and so you, again, make the same step we did in the last one, where it's 3 times the lot, and you get, therefore, is a multiple of 3 again. So we're going to do it one last time for 3m plus 2 on the next slide here, because that's going to be 2 away from a multiple of 3, and then that's going to be all the possibilities. Right, so we've got this set up, and we're going to see that we're going to use the 3m plus 2. Remember, we're using implies. M is a whole number, and we pop that into the equation again. That's the n cubed minus n version. Okay, we're going to expand it out again the same way. You can, of course, do it whichever way you want. If you want to do the long multiplication of this times 3m plus 2 squared, that's fine as well. But we're going to use Pascal's triangle once more. Expand it all out, and then we get this line here, and then we're just going to simplify to try to do exactly the same thing we did in the last two. Right, so we have a slightly different version here where this bit doesn't cancel, but it's still divisible by 3, so make sure you're just saying 3 times everything. Put your statement at the end, and now we've run through all possibilities, so we need the final concluding statement for the whole proof. And quite often on these last statements, you end up just rewriting the thing anyways, just to make it very clear that you've got to the end. Always try to highlight what you've done and sort of underline your final answer. So that's the first proof that we're going to get in A levels, proof by exhaustion. Phew. So we got through that one. They can take a long time to do these proof by exhaustions, but they are kind of the same each time. You will get much better with these if you see a lot of examples and you do a lot of practice with them. They're like adding different tricks to your bag that you can use, or tools to your tool belt that you can pull out at any time. But you kind of need to see a lot of these first before you get very good at them. Okay, so no more exhaustion, thank goodness. If you found this helpful, please like and subscribe. The next ones are going to be proof by contradiction. Should follow on the next video. Okay, bye-bye.